In this lesson, we're going to learn about L'Hopital's rule. L'Hopital's rule is an excellent tool that allows us to evaluate some limits analytically much more quickly and much more easily using differentiation. In fact, a lot of times students get a little upset when they learn L'Hopital's rule because it makes limits that we did earlier in the class so much easier that they wonder why we didn't teach it in the first place. And the answer is just simply, we didn't know how to differentiate. And now that we do, we can take advantage of this. The rule states that if the limit as x approaches some value of f of x divided by g of x is equal to 0 over 0, or that limit equals positive or negative infinity over positive or negative infinity, then the limit can be evaluated by taking the same limit as x goes to a, the same limit point, of the derivatives of f of x divided by g of x. And want to point out here, this isn't the derivative of the entire function, it's the derivative of the numerator divided by the derivative of the denominator. So it's no quotient rule is needed here. So this is a really nice rule. It does apply to other types of indeterminate forms, and an indeterminate form is the 0 over 0. That's an indeterminate form. It doesn't tell you the value that you're actually looking at. It could mean infinity, it could mean 0, it could mean any constant number. It just doesn't tell you any information. We took it to mean that there's probably some algebra that we could have done to perform the limit earlier in the class, but now we're taking it to mean that L'Hopital's rule can be applied. This will apply to other types of indeterminate forms as well, but you often have to do some algebraic manipulation first. And those other types of indeterminate forms are these. So 0 times positive or negative infinity. Usually 0 times anything is just 0, but 0 times infinity doesn't have any meaning. 1 to the infinity power is an indeterminate form. Generally, 1 to any number is 1, but 1 to infinity is an indeterminate. As well as 0 to the 0th power, infinity to the 0th power, and infinity minus infinity. So all of these are indeterminate. And to give you an idea of how this works, here's a concept. So L'Hopital's rule works by comparing how quickly the values of the numerator and the denominator are growing. So we examined limits like this in the past when setting up rules for evaluating limits of rational functions as x was allowed to increase to infinity. So for instance, as a reminder, we compared the numerator and denominator's degrees of those rational functions. And if the numerator's degree was larger, then the limit went to infinity. So the idea is, if the degree in the numerator is larger than the degree in the denominator, the numerator is growing much more quickly than the denominator, and therefore the value of the fraction is going to rush off to infinity. If the denominator's degree was larger, then the limit went to 0. And the logic there is, if the degree in the denominator is larger, then the denominator of that fraction grows very quickly compared to the numerator. And as you go to infinity, the entire fraction goes to 0. Or if the degrees were equal, the limit went to the ratio of those leading term coefficients, because in that kind of a situation, they're going to infinity at about the same rate, and they kind of cancel each other out. Now, it's not exactly how L'Hopital's rule works, because we're not exclusively examining limits where x is approaching infinity, but it just gives you some intuition as to how it does work. So let's consider some limits here. So first off, the limit as x approaches 3 of x squared minus 9 over x minus 3. These two particular this particular limit, if I start off plugging in the value 3 squared minus 9 over 3 minus 3 gives me 9 minus 9 over 3 minus 3, which is the indeterminate form 0 over 0. So in the past, what we were told here is that this is an indicator that some sort of algebraic reduction can be done so that we could still evaluate this limit. So as a reminder, in this case, we could take the limit and factor the numerator into x plus 3 times x minus 3 and put that over x minus 3. The term x minus 3 cancels out. Now when we plug in the limit value of 3, it's 3 plus 3, which is 6. So we get an answer that's determined. It's not an indeterminate form any longer. But what L'Hopital's rule is telling us is that when we end up with a limit that becomes 0 over 0, we can now take the derivatives of the numerator and denominator. So the derivative of x squared minus 9 is 2x. The derivative of the denominator is 1. And generally what we do to indicate that we use L'Hopital's rule from one step to the next, we put a little L'(h) over that equals, just to indicate how we're supporting the work that we did. Now, 2x over 1, if I plug in 3, it becomes 2 times 3, which is 6. That's much easier to get to the answer than what we did with factoring, because it's usually just as easy even if square roots or fractions or anything else is involved. The derivatives are usually pretty straightforward. Here's another example. The limit as x goes to 0 of sine x over x. And in this particular case, if I plug in 0, it's sine of 0 divided by 0, which is 0 over 0. So that tells me that there's some sort of algebra probably that I could do so that I could rearrange the form of this in such a way that I can evaluate this limit. But it's not always so obvious what that algebra might be. L'Hopital's rule, it doesn't matter. We end up with a limit that results in the type 0 over 0. So we just say, all right, using L'Hopital's rule, this is going to be the limit as x goes to 0. We take the derivative of the numerator, so the derivative of sine is cosine, and put it over the derivative of the denominator, and the derivative of x is just 1. Now, the cosine of 0 is 1. We didn't have to use a table method. There wasn't advanced algebra involved. Very straightforward. L'Hopital's rule is generally a very welcomed rule into mathematics. And these just tell us exactly what I was explaining through the examples. Let's take a look at a proof of L'Hopital's rule, at least one special case of it, just to get an idea of how it works. To begin, we need to set up a couple of functions. So we'll suppose that f of x and g of x are differentiable functions, and x equals a is a particular point on their interval where f of a is 0 and g of a is 0. We'll assume that f prime of a and g prime of a both exist. Now, what we want to show here is that the limit as x approaches a of f of x over g of x is equal to f prime evaluated at a divided by g prime evaluated at a. one thing that we know right now, just the way the problem is set up, is that f evaluated at a and g evaluated at a, when we divide those two, we end up with 0 over 0. All right, that was what the statement of the problem says here. So we're going to try and show this. All right. So let's start with the derivatives. We'll start with trying to figure out what does f prime of a over g prime of a look like. Because we know a little bit about derivatives. We have the limit definition of derivatives, these sorts of things that we can work with. That's what we're looking for, something that we can get started in. So this right here, each of these is a limit. So it's a f prime of a is the limit, and I'm going to use the form as x goes to a of f of x minus f of a divided by x minus a. Now this is not the form using delta x, but it's the same concept. It's still the slope of a secant line, and we're taking the we're looking as the limit value approaches the point of interest. So we're looking for a tangent line. So it's still a derivative, even though it's not the one using the delta x. Now we can divide that by the limit as x approaches a of g of x minus g of a all over x minus a. Okay. Now, these limits exist. We made a supposition in the very beginning that these limits exist. And because these limits exist, we can actually change them into a single limit. We can make this the limit as x approaches a of this whole thing divided. But instead of writing this whole thing divided, what I'm going to do is write it out as multiplied. So f of x minus f of a all over x minus a times, instead of dividing by g of x minus g of a over x minus a, I'm going to invert and multiply. So x minus a over g of x minus g of a. The reason I'm doing that is because I can see this term x minus a, and I can get that to cancel out. Okay. Now, what I have at this point is the limit as x approaches a f of x minus f of a over g of x minus g of a. Okay. Now, in order to get to the next step in the problem, what we have to do is go back to a couple of things that we decided upon from the very beginning. We decided from the very beginning that f evaluated at our limit point is 0, and g evaluated at our limit point is 0. So if you'll notice, I have, as part of my limit right now, f evaluated at my limit point. So this part right here is 0. That's what we decided from the very beginning. And same for g of a, which gives me the limit as x approaches a of f of x over g of x. So what that means is we started with this being f prime of a divided by g prime of a. So we've kind of made a complete sentence here, and we can now say that the limit as x approaches a of f of x over g of x is equal to, and if we went back through that statement of sentences that we did here to where we began, which was this step right here, that is equal to f prime of a over g prime of a. So we can just take our limit. We can evaluate the derivative of the numerator and denominator and take our limit at that point. Let's see some examples. So let's evaluate the limit as x goes to 0 of 4x squared minus 5x over 4x minus 3x squared. Now, it should be obvious that if you plug in 0, you're going to get the form 0 over 0, because all the x terms would disappear. So we're going to evaluate this limit using L'Hopital's rule. So this would become, based off of L'Hopital's rule, the limit as x goes to 0, the derivative of the numerator, which would be 8x minus 5, over the derivative of the denominator, which would be 4 minus 6x, just using rules of differentiation. And now, if you plug in x equals 0, we get 8 times 0 minus 5 over 4 minus 6 times 0, which is negative 5/4. No tables needed, no advanced algebra, just a very simple set of derivatives that have to be performed. Let's evaluate the limit as x goes to infinity of e to the x over x squared. For this particular limit, if I plug in the limit point, which I'm not technically plugging in infinity, it's just I'm allowing x to grow infinitely large. And as x gets larger and larger, e to the x goes to infinity. And as x gets larger and larger, x squared goes to infinity. So this is the type infinity over infinity. And so what that means is it's an indeterminate form, but not one that we have to do any sort of manipulation with. We can still use L'Hopital's rule. So this will become, after we apply a round of L'Hopital's rule, the limit as x approaches infinity, e to the x is its own derivative, so that's just e to the x. X squared's derivative is 2x. Now again, if we plug in, or if we look at what happens to this limit as x goes to infinity, the numerator would be infinity, the denominator would also be infinity. But there's no reason that we can't apply L'Hopital's rule a second time. Sometimes you might have to do it 4 or 5 times until you can finally get a result. But if you'll notice, I went from a square in the denominator to a linear term in the denominator, so I know that I'm getting closer to something happening. So I'll apply it again. Limit as x goes to infinity, e to the x over 2. And now the 1/2 is just a constant multiplier. We could come out, and we're just looking as the function e to the x going to infinity. What's happening there? It's going to positive infinity. So this limit is going to infinity. Here's another example. The limit as x approaches 0 from the right of x times the natural log of x. Now, in terms of L'Hopital's rule, we're getting the result for the entire limit, which means you get the left-hand side of the limit and the right-hand side of the limit when you evaluate L'Hopital's rule. So if you just need one side, you're not going to change anything. You're still just going to apply the rules the same exact way. But your result is just in terms of, okay, this is just one side, but it doesn't change your mathematics at all, which is nice. So the limit as x goes to 0 from the right of x times the natural log of x. And the reason we have to come from the right here is because the natural log of x is not defined for negative numbers, so we're just staying in the realm of positive values. The thing that happens here, if I try to plug in 0, is when x is 0, it's just 0. When x goes to 0 from the right of the natural log of x, the natural log of x, when x goes to 0, is going to infinity. So this is really of the type 0 times infinity, which is one of our indeterminate forms. It's not the type that L'Hopital's rule can be used outright with. We do have to do some manipulation. We either have to have this of the form 0 over 0 or infinity over infinity. And usually, especially this case, it's not a difficult thing to do to transform it. So for instance, let me change this into the limit as x approaches 0 from the right of the natural log of x over 1 over x. This is the same thing. So usually we would simplify this situation, natural log x over 1 divided by x. And we would simplify it by inverting the fraction and multiplying, which gets us back to x natural log x. But I'm rewriting it in this form instead because what that allows me to do now is when I look at what happens as x is going to 0, the numerator, that natural log, is still infinity, but the denominator has an asymptote at 0. It's infinite as well, which means in this form, L'Hopital's rule will apply. So I can use L'Hopital's rule and say that this is the limit as x goes to 0 from the right. So indicate that I'm using L'Hopital's. The derivative of natural log x we know to be 1 over x, and the derivative of 1 over x, you might have to go over to the side and allow that to be x to the negative 1 power, then bring the negative 1 down and use the power rule. But what you'll come up with is this is negative 1 over x squared. And to see if this limit's going to work at this point, we need to do some simplification first. So let's invert and multiply. So this would be the limit as x goes to 0 from the right of negative x squared over 1 times 1 over x. So one of these x's goes into one of these, leaving me an x. So I now have the limit as x goes to 0 from the right of, looks like just negative x remains. And if you put in 0, you'll just get 0. So even if L'Hopital's rule won't apply initially, you generally can do some algebra to make it apply, which is great because otherwise we would have to resort to a table to evaluate this, because I don't know any particular algebra that we could have used other than without the use of a table. So it saved us that much time. All right, let's try the limit as x goes to negative infinity of x times e to the x. All right, so the limit as x goes to negative infinity of x e to the x. If I allow x to go to negative infinity, so the first function, I cringe at doing this, but I'm going to do it anyway. I'm just going to let x be negative infinity, and then I'm going to say e to the negative infinity. Because ultimately I'm not plugging in infinity, I'm just observing what happens to these functions as we go to infinity. So as x goes to negative infinity, it's just negative infinity. But e to a negative power, what happens there is, well, I'll just leave it as this. So e to the x looks like this. This is the graph of e to the x. And as x goes to negative infinity, which is over this way, so we're going toward negative infinity, this is approaching 0. So this is actually the form of infinity times 0, which is an indeterminate form, but it's not one that we can initially use L'Hopital's rule with. So we have to do a little bit of manipulation. And generally all that means is we could take the x and make it divided by 1 over x. Or we could take the e to the x and put it in the denominator by making the exponent negative. That's generally all we have to do. So let's try it here. Last time I worked with the algebraic part. This time I'll work with the exponential. So limit as x goes to negative infinity of x over e to the negative x power. Now, as we observe x going to negative infinity, this is now of the type infinity over infinity, because e to the positive infinity goes to infinity. All right, because looking at this graph over here, as e goes to positive infinity, the graph itself is going to infinity. And because it's of the type infinity over infinity, L'Hopital's rule will apply. And pay attention that I am writing a limit every single time before my function until I have actually evaluated the limit. You need to make sure you do that, because if you don't put the limit at each stage in the process, your instructor will often take off credit for that sort of thing, because it's not a number until you've actually evaluated the limit. So let's see. We need to take the derivative of the numerator, which would be 1, put that over the derivative of the denominator, which would be negative e to the negative x. Now, if I change this around, make this the limit as x goes to negative infinity of negative e to the positive x. I'm just making this a positive exponent now because my algebraic piece is gone. It probably makes more sense to write it this way. So again, e to the x as we go to negative infinity is going to 0. So this now evaluates to 0. Here's another example. The limit as x goes to 0 of x to the x power. Now this is a slightly different type of function that you've probably never seen before. And it's not really a polynomial, because for polynomial functions you have to have a constant exponent. And it's not really an exponential function, because for an exponential function you have to have a constant base. This, the base and the exponent, are variable. It grows faster than both the polynomial and the exponential, but we're concerned with the limit of this function and seeing what happens here more so than how it grows or anything of that nature. In order to do this, we don't really have any, it's an unfamiliar function that we don't really know any algebraic properties of at this point. So the best we can do is try and manipulate it a little bit and get it to a point that we can actually work with it in some way. Because the problem is, if I put in 0, I'm going to get 0 to the 0th power, which in fact is an indeterminate form. I gave that earlier in the lecture. But it's not one that L'Hopital's rule will apply to directly. And it doesn't really matter, because we can't be guaranteed that we could do the derivative of this function in the first place. So we need to find some way of manipulating it. Since it has an exponent, logarithms were designed to be the inverse of exponential functions. So I think using a logarithm probably is our best bet here to get something started. So let's try, we'll define a function y and call it x to the x power. Now I can take the natural logarithm of both sides of this equation. You can do that for any equation. And the reason I'm doing it here is because I can now use properties of logarithms to say that exponent of x can be a multiplier on my logarithm. Okay, that's very nice. Now, I might be able to do something with that. In fact, from an earlier session, an earlier example, that is, I did see that the limit as x goes to 0 of x times the natural log of x. And I'm not going to work through the details here because we did it just a few examples ago. X times the natural log of x, we saw that that limit resulted in 0. Okay? So what that means now is the natural log of y is equal to 0. And if I solve for y, I would have to get y out of the logarithm. So I could raise both sides of this equation to a base of e, or using a base of e, so that I get y equals 1. And y was my original function, and so through the limiting process, since I did the limit of this, it sort of implies that the limit of the original function is what I just came up with as 1. So sometimes you get more advanced problems like that where you do have to do some work with logarithms in order to use L'Hopital's rule. But for the most part, polynomial rational functions are very simple. Any type of trigonometric functions generally aren't that bad either, so long as you can actually evaluate the trig functions at the point that are required. So most of the time, L'Hopital's rule is a welcome change.